Hello, my name is Martin Ebert. I work as System Simulation Engineer at RV. Today I want to present my presentation with the topic evaluation of low-frequency NVH phenomena in electric vehicles using a modular drivetrain library from SimulationX. My presentation is structured as follows. Firstly, I look at the problem and the motivation. After analyzing the problem and considering the NVH simulation model, I describe at the third point the simulation model structure. Fourthly, I will explain my evaluation method for such phenomena. After that, I compare the basic and the advanced simulation model with regard to a number of important criteria. In the sixth point, I will show the optimizations performed and are possible with the IRB's optimizer. I will also talk about the model exchange via the FMI interface. Finally, I will summarize what has been shown and give a short outlook to further approaches. Before I get to the motivation, I would like to briefly describe the problem to be simulated. In battery electric vehicles with double decoupled electric drive axles on the front, disruptive vibrations in the low frequency range up to approximately 15 Hz occur during driving special maneuvers, as well as full load braking and full load acceleration on the wave track or the manual cover section. These vibrations phenomena impair the acoustics, the driving comfort, and the drivetrain components and the support frames. My motivation. Applications of the best MBS simulation method that maps this problem with the simplest possible simulation models in order to detect weak points in the early development phase. There are several CAE methods for realizing this vibration problem. Due to the fact that this is a low-frequency NVH phenomena, it can be modeled with a 1D MBS model. IRV's modular driveline library is ideally suited for this purpose. The rigid body vibrations of the E-axle and the subframe are also very important for the analyzing of this problem. For this reason, 3D rigid bodies of the E-axle and subframes, as well as their mounts, are modeled in the 3D MBS and covered with a 1D drivetrain model. Before I speak over the construction of the required MBS model, I want to analyze the vibration problem. Measurements show high torque peaks in the drivetrain components and in the E-axle and subframe mounts. These appear to be caused by high torque fluctuations in the drive shafts and the resonance behavior of the 3D rigid bodies. Possible causes for the protecting drive shafts are: the high torque fluctuations of the drive shafts appear to be generated both by the longitudinal dynamic of the vehicle and by the vertical dynamic of the wheels. These occur as a result of excessive stick-slip excitation due to the excessive braking and drive torques. Furthermore, the vertical dynamics of the wheels appear to have an influence on the fluctuations. This means that the unspring masses are periodically excited by traveling over uneven road surfaces. This can lead to a resonance frequency of the unspring mass at certain vehicle speeds. As a result of the resonance, the contact pressure of the wheels fluctuates and the stick-slip effects occur to a greater extent. On the next slide, I want to show the common simulation model, also components. The 1D drivetrain contain all relevant mass moments of inertia and the torsional stiffnesses from the E-motor rotor to the wheels. By this, all important torsion and natural frequencies are included in the simulation model. The majority of the drivetrain model was built with elements of the IRV's modular drivetrain library. To map the 3D rigid body modes of the E-axle and the subframe, these components are modeled in the 3D MBS. Using elements of the 3D MBS mechanics library and coupled to the 1D drivetrain over the mount elements which are contained in the 1D power transmission library. The mount stiffnesses of the E-axle and subframe mounts are taken into account using force displacement diagrams for all space directions. There are two different ways to model the excitation of the uneven road surface and the right sliding dynamics, vertical dynamics. And one simply, where the rear ground context, the rear suspension and the car are modeled as elements of the 1D mechanics and 1D power transmissions library. In the advanced model, these components are constructed using elements of the library driving maneuvers. This slide shows a basic simulation model with a simple 1D rear ground context, the rear suspensions, and the car. The 1D drivetrain model contains the E-axle model on the front and the rear axle, the drive shafts, the wheels, the rear ground context, the car to simulate the torsional and longitudinal system behavior. The 1D model of the E-axle is coupled with the 3D model of the rigid bodies and mounts on the front and on the rear, in order to be able to simulate the combined resulting rigid body and combined network frequency and vibration moves. The vertical models for each rear suspension used to simulate the degrees of contact force due to the road excitation and the vertical resonances and dynamic load distributions. The advanced model is identical up to the wheels. New are the MF tire wheel models. This 3D car with a simplified rear suspension. These components are used to simulate the degrees on contact force too. Furthermore, they realize the resonance behavior of the unspring masses and the dynamic load distribution of the car. On this slide, I would like to present our evaluation method for such phenomena. Once the overall simulation model has been set up, the first step is to carry out a natural frequency analysis. The natural frequency analysis shows which frequency in the critical range from 10 to 15 Hz. By analyzing the animation, the deflection, the kinetic and potential energies, more information are obtained over the system's behavior. In the second step, the relevant driving maneuvers are simulated to validate the simulation model with measurements and obtain the corresponding results. The relevant results would be evaluated in this third point. Analyzing the drive shaft torques, the wheel speeds, the mount displacement, and the mount forces reveals high vibration amplitudes in the resonance range. These are caused by a coupled vibration between the 1D drivetrain and the 3D axle. This causes the E-axle to oscillate up to the resonance frequency. As a result, the progressive stiffness range of the mountings is reached and resulting in high force peaks. This can be critical for NVH behavior. After presenting the evaluation method, I would like to compare the basic and the advanced simulation model. Both models deliver good results. The data procurement effort for the advanced model is much higher. However, the validation is easier here. The advanced model can be used for the straight and cornering maneuvers. On the contrary, the basic simulation model can only be used for driving maneuvers that describes driving straight ahead. If all required data are available, I will prefer the advanced simulation model. As the tire slip represents more the reality through the MF tire files, and the 3D vehicle are also more closely to the reality. Now that I have talked about the model structure, the evaluation method, and the comparison of the two simulation models, I would like to discuss the optimization options. IRV has an own optimizer, which is contained in the IRV engine toolbox. The optimization can be used for the reduction of the mount forces. For this, the optimizer moves the mount positions in the specified space constraints. After optimization, all variants are evaluating using weighting factors. The optimizer could also be used for evaluation of the mount characteristics or in the early development phase, the mounting concepts. In SimulationX, it is also possible to exchange models with other software products over the FMI interface. For example, partial models can be transferred to the third system SimPack. Based on this, an existing torsional vibration model of an E-axle for the torsional excitation of the wheel suspension and drivetrain is transferred to an FMU 2.0 for co-simulation. This is then later integrated into a SimPack model and used further. Before the FMU is transferred to SimPack, it is tested in a SimulationX drivetrain model. The quality of results and the simulation time can be influenced by adjusting the communication step size of the FMU, what you see here. After the integration of the FMU in a SimPack model, the functionality and quality of the results are evaluated as very good. Now, on the last slide, I want to give a short conclusion. New challenges for the NVH behavior of battery electric vehicles compared to conventional drives. SimulationX software is very well suited for NVH evaluation by the components, libraries, the driving maneuver libraries, and the interfaces to other products. Low frequency phenomena can be represented in the simulation model by coupling the 1D torsional drivetrain and the 3D mounting components. Evaluation of the simulation model according to the IRV methodology for two levels of details show very good agreement with vehicle measurements on the test tubes. High acceptance of the simulation method in the early development phase process through optimization and interfaces to other specialist areas. In the next step, we want to integrate an AA driver model into the simulation models and look for further new steps.